All right. So good evening. Right. So this is fundamentals of compressible flow course conducted by NPTEL. Right, and we are in the sixth live tutorial session of this particular course, and the topics we would be discussing in this particular session are expansion waves and oblique shocks. So basically, we shall just get introduced to these two concepts in this particular live tutorial session, right? And the instructor for the course is Professor Niranjan Sahu from IIT Guwahati, and myself, Aditya Sharma. I am a Prime Minister's Research Fellow, and under that fellowship only, through that fellowship only, I am conducting these live tutorial sessions. All right, I also belong to IIT Guwahati, right? So we shall start this particular session in, I believe, a couple of minutes. Let's wait for another 3-4 minutes and then we shall start the session, today's session. Thank you. Okay, so let's start with today's session, right? So Ginny, you are there, right?
Yes.
Okay, thank you. All right, so as I have mentioned, so we will be discussing the agenda of today's session is expansion waves, and then this is oblique shock waves. So as this course is compressible flows, right? So here also in these two terms, we shall be dealing with uh, flows where there is Mach greater than 1, but then there are few tweaks to that flow, and because of those tweaks only, so the flow is behaving in a particular way. So that particular thing we shall be discussing in this session, right? So we shall see how the things unfold, right, as we move ahead, right? So first of all, as we have been doing earlier, so we shall quickly revise the topics that have been covered in this week. Sorry, this should have been week 6, right? Okay. So all right. So the first topic was this expansion waves, right? And then there is one subheading related to Mach wave. So what is an expansion wave, right? So previously we have studied normal shock. Okay. So this is, we studied normal shock, but then now we are studying expansion waves, right? So in normal shock, what was happening that at Mach greater than 1, right? So if this is a particular conduit, right, in which there is flow which is with Mach greater than 1, we experience some shock right here. So this was about normal shock. But in expansion waves, what is happening is, so suppose this is a surface, right? So what we are doing is we are changing, giving a direction to the surface, right? So suppose flow is moving in this direction, right? With some m greater than 1. So what we did, we just tweaked the surface, and by virtue of that only, we get something that we call, so flow direction will be in this direction, right? So what we get in that case is expansion waves, right? And cumulatively, because these waves are continuous, so we term it as also a fan, right? Expansion fan. All right. So then we studied these formation of how the expansion waves are formed, right? So if you see, right? So if gas is here and this is a piston, gas has some initial pressure, right? So what we in this normal shock modeling, what we were doing is to understand to understand the normal shocks. What we were doing, or what we did is, we moved the piston in this right direction, right? Same figure, right? Same elements of the figure, but the change here is that we will be moving this piston in left direction, right? So obviously, if this piston moves in left direction, right? So as a layman, we know that eventually when this gas in this particular conduit comes into rest, the pressure at the end, final pressure will be less than the pressure we had in the initial phase. All right. But before reaching to its final stage, right, there is gap between initial and final phase. So in that gap, there are some transitions, right? So this how this transition takes place. All right, what happens in the meantime when this transition is taking place? So when we look into that, we find that such transition has expansion, right? So the this gas in this particular conduit is expanding in a way, right? Because pressure is decreasing, right? So that is fundamentally expansion. But then, for example, if we change, let us say, right? Let us say this is the initial, right? This is the initial position of the piston. Then we moved it to left, right? And then this is the second position of the piston, right? This is the second position of the piston. In that case, a wave will travel in this right direction. Wave travels in right direction. Okay. Expansion wave. It's just a communication by a communication wave is being sent in the gas that this particular gas is expanding, right? So it happens in a form of a wave. All right. So in the second step, if we move this uh, particular thing further left, right? So if this is 2, this is 3. So again there will be, so if this is the expansion wave, right? If this is the expansion wave, so then let's say this is expansion wave 1. So this is expansion wave 1, and this is EW2, right? So what here is happening is that in the shock waves, what was happening? So just for comparison, right? So because in the lectures also you'll find somewhere it is mentioned that these expansion waves are antithesis to shock waves, right? So from uh, that perspective, this discussion correlates, right? So what there was happening is that if one wave is moving, right, then another wave is moving. So this another wave's speed of this propagation is higher than the previous wave, right? So at some point they will collize, right? At some point in future, these waves collize. All right. But in case of expansion waves, this is not the case. All right. What happens is that that because all the property changes that happens in case of expansion waves are totally opposite to these normal shocks or shock waves. So in that case, the movement of these expansion waves, the propagation speed of these expansion waves, right, is less than their previous expansion wave. What I mean to say, for this EW1, the propagation speed will be greater than EW2, right? So in any case, these two waves are not going to collize, right? So when I was saying that we get a expansion fan, right? So by that we only mean this only thing. We mean that if a flow turns, right, so there is expansion, right, but then there is continuous expansion of that flow, and the uh, first wave, right, that has traveled downstream. So if there is some another wave coming from upstream, there is no chance it will collize, right? So these will pile up like this, like this, like this. These will expansion waves will pile up, right? So in that scenario, we get a fan type of like structure, right? Uh, we encounter a fan like phenomena, right? Phenomenon. So that we call as expansion fan. All right. So this is this formation how the expansion waves form, right? So then expansion waves have been discussed in terms of isentropy, right? If the this turning of the flow is smooth, right? So in this way it has been presented. So how like we deal with expansion waves when there is this isentropic condition is there, that has been discussed. All right. All right, then this is very important. Next topic is very important from the perspective of expansion waves, right? So the next topic, uh, as it has been written here, is Prandtl-Meyer expansion waves, right? So the main point to here taken into consideration is this function, right? The Prandtl-Meyer function. So numericals often come from this particular function, right? Based on this particular function, these numericals do come, right? So we'll just, it's important that we understand the various elements of an expansion wave in terms of its graphical representation, right. So I'll just draw this so that when somebody is encountering a numerical based on Prandtl-Meyer expansion waves, so these terms should be clear, right? So I'll just draw this wall and this turn, right? Sorry. So if this is the flow direction, right? So what we get is we get these two Mach lines, right? This is forward Mach line and this is rearward Mach line. All right. So you just draw these dotted lines, right, in the direction of the upstream flow direction, in the direction of upstream flow, right? So here, what happens is this is your Mach angle for the this upstream condition, right? And then this is your Mach angle for the downstream condition. All right. And this angle is your deflection angle. So with what angle we are deflecting our flow, this is that theta, right? And the others are mu m1 and mu m2. Other than that, there is one more angle, right, which is fan angle, right? I'll just draw another diagram. Right? So if this is the flow direction, so this is the fan angle, right? So angle between two these Mac lines is fan angle. So when questions are asked based on these particular terms, so one should be clear, right? So I am like I want to calculate which part of this particular diagram I need to calculate to solve a particular question. So from that perspective only, I have drawn these two figures. All right, Ginny.
Nice.
Yes. Okay. Thank you. Okay. So then there are fundamental equations of PM waves, right? So this has been written. All right. So I'll just not go into what has been numerically put forth in this particular section, all right, but then this is basically the fundamental equations of expansion wave. So mathematically, if we have to solve expansion wave, we need to take help of fundamental equations, right? So this is from that perspective. And all right, and then there are flow properties of PM expansion waves. So across expansion wave, how the pressure, density, temperature, Mach, how they behave, this has been covered in this particular section, right? So for example, the pressure, the static pressure, right? Static pressure, what happens, because it is clearly, it is the name is mentioning that it is expansion, the pressure, the static pressure uh, decreases, right? And same is the case for temperature also, right? Static temperature decreases, and then density also, static density also decreases, right? All right, and then the main major point in terms of flow properties is that across expansion fan or expansion wave, there is increase in the Mach number, right? There is an increase in the Mach number when we move across a expansion wave, right? So this is about lecture 14. All right.
Yes.
Okay. Okay. Right. So moving on to lecture 15, right? So lecture 15 also is very important. Oblique shocks. We have discussed normal shock waves. Here we are discussing oblique shock waves. So what is difference between normal shock waves and oblique shock waves? Right? As the name also suggests, there is obliqueness in the shock wave, right? So flow is moving in particular. Let us suppose flow is moving in particular direction. So in this case, the shock wave won't be perpendicular to the flow. Right? The shock wave will be at a particular angle to the flow, right? So if we want to put things in perspective, right, to see, visualize things, so I'll show this, right? Oblique shock waves. Let's first see what are the topics we have, right? So there is oblique shock waves, and then there is comparison of normal shock waves and oblique shock waves, and then there is Mach angle and shock wave angle. Shock wave. So this shock wave angle decides the obliqueness of a particular oblique shock. Okay, so oblique, this shock wave angle is a very important parameter as far as the oblique shocks are concerned, right? Right. Okay. So Then there is governing equations of oblique shocks, which is like pretty similar to normal shock waves. Okay, but then there are few like one important point that we need to consider. We need to take into consideration while we are studying normal shocks, and how that is similar to while we are studying oblique shocks and their governing equations, and how they are in a way similar to normal shocks, that we shall see in this particular topic, right? And then there is this theta beta m relation, right? It's also a very important relation when we are studying oblique shocks. We cannot dare to miss this particular relation, right? Because our numericals, they rely on they may rely on this particular relation. So we need to also remember this particular relation, right? From the exams point of view, I'm telling you. And then there is this last topic, that is pressure coefficient. So in lecture 15, a expression, right, a formula has been given for pressure coefficient, right? So pressure coefficient, all right, it's important. Pressure coefficients are important when we are studying this aerodynamics, right, or fluid mechanics for that matter. But then when we are dealing with oblique shocks, I haven't come across questions based on pressure coefficients, right? But then we should know, because this, as this has been included in the content, right, of uh, this topic. So at least we should know about this particular. We should touch upon this particular topic, right? Okay. So then there's oblique shocks and governing equation and theta beta m, right? Okay. So let me just do it. Okay. So this is oblique shock waves, right? All right. So what we do here is, so in expansion fan, what we were doing is, if you see this expansion wave, we moved this particular flow direction, right? We moved this away from the flow direction. We moved the flow away from itself. So suppose if this is the flow direction, right? So we move the whole flow away from itself, right? All right. But then in this case, but if we move this flow towards itself, right? So in that case, the thing we get is an oblique shock, right? So if I draw it, right? So, oh, I made a very big slant. So this is theta, right? Okay. So if flow is coming in this direction, right? So obviously, no doubt, from a very layman's perspective, this flow will move in this direction, right? Because we have like tilted this wall upward, right? But then because this is not a very normal kind of flow, in this case, the flow is supersonic, right? So what happens is with this direction, right, we get this oblique shock. We here get an oblique shock, right? This type of oblique shock we get, right? So the flow direction changes and we get an oblique shock. So this is this before the oblique shock conditions and this is after the oblique shock conditions, right? Then there are these directions also related to oblique shocks, right? So I believe I'll discuss that when we are discussing numericals, right? When we are discussing a numerical based on oblique shocks. So in detail, I shall discuss it later, right? So this is particular like to picturize how the oblique shocks are, right? I just drew this particular diagram, right? So this is about oblique shocks, right? Just to picturize. All right. So then there is these relations are there, right? There's Prandtl-Meyer relation also. So I'll just not write Prandtl-Meyer relation here. Okay. What I'll do is, but obviously, okay, I'll write this. Just let me just write this theta beta at least relation, right? So this is tan theta equals to 2 cot beta. All right. Okay, so this is the theta beta relation. All right. So I'll just conclude this topics covered part here only, right? And now that we have discussed these topics briefly, we should move on to questions, right? Right. Okay. Okay. All right. So I haven't discussed. I didn't discuss governing equations because I just, as I just said, that we have a numerical in line based on these oblique shocks. So I'll discuss that at that point only, right? Okay. Okay. I'll discuss in this. Let me just write this. Okay. So I'll discuss these governing equations at that point only, right? And then there is expansion wave numerical, and then there is also this theta beta m. All right, this is theta beta m numerical. Right. All right. Okay then. So this was about the topics that have been covered this particular week, right? Again, this is week 6. Apologies for this, right? So now we move on to questions. So I have this 16 total 16 questions I could like figure out from the content, right? So 13 are theoretical, and then there are three numerical type questions, right? So in these numerical type questions, I have covered all these major like expansion wave relation, Prandtl-Meyer function I have covered in it, and then this Mach wave across oblique shock, right? So we shall discuss that in one numerical, right? And then there is one numerical on theta beta m relation. So these are three numericals we shall discuss, right? And before that, we will just have discussions uh, based on just concepts, right? Theory based questions we shall discuss. Okay, then. So this is based on concept of expansion wave, right? So this is expansion wave question, right? And the question says that the main bulk of supersonic flow dash when it encounters a compression corner, right? So there are 2 points. One is that the flow is supersonic, right? Okay. And then there is this compression corner, right? So now these two terms are important, right? Right. So let's see the options, right? Okay. Right. So when I write topics, right? So I do it based on the content where I found that content, right? There are chances that it's not directly, the question is directly not of that topic, but the content uh, is from this particular topic of this particular week's lectures, right? Yes. Okay. So what is the answer to this question?
Yeah.
A. All right. Okay. So there are four options. Okay. So this is, first of all, this is a supersonic flow. Okay. And then the question says that it is a compression corner, right? So the question itself has already told that there will be compression in this flow, and that too by means of a corner, right? So for that matter, if we see the compressible flows, there are two cases. One is where flow is expanding, and then there is another case where there is compression, right? So in also, if you remember, in normal shocks also we saw that normal shock mm, is a case of compression, right? So same is the case with what, oblique shocks, right? Because the question here has mentioned that it's a corner, right? So by means of corner, compression is taking place somehow, right? So from our previous knowledge, we already know that if there is a corner, something like that, right? If flow is in this direction, and if this is our corner, right? So the flow is moving towards itself, right? And this moving towards itself leads to compression. All right. So just as has been answered that it will move towards itself, right? So there are options, it turns away from itself. That is not the case, right? Uh, then there is turns according to the flow conditions, right? So the question says that it turns, like, it can move in either, it can be, this type of compression can happen by either means, right? If by moving this corner upwards or moving it downward, right? But that is not uh, uh, right? So it is also saying that it doesn't change the direction, but then that is for this normal shock, right? For, because the question already has mentioned that it's a corner, right? So in any way the flow is going to move in some direction, right? But because it's a compression corner, so it will move towards itself, and in that case it's an oblique shock, right? And the answer is A, right? So this was first question based on the concept of oblique shocks, right? Sorry. Okay. So if you see, yes, answer is A, right? So let's move on to next question. So again, this question is from this topic, right? Concept of expansion wave. Right. Okay. So the question says that a supersonic flow can expand to a lower Mach number. Okay. Through turning away from itself across a corner. Okay. So there are a couple of things. First of all, the flow is supersonic, and then it is expanding, then to a lower Mach number, then turning away from itself across a corner. So the previous question was based on a corner, right? And this particular question is also based on a corner. All right. So if we see the options, right? So this is a true or false type of question. Please read it carefully and come up to an answer.
False.
False. Okay. Ginny says it's false. Okay. Let's see this. Right. Let me grab some water first of all. Then let's discuss this. Okay. So the flow is supersonic and then it is expanding. So there, let's just note this down. First there is supersonic and then there is expanding. Then there is Mach number is reducing. Then turning away. Right. across a corner, right? So if you see this point 1 and 2, right? So first of all, the question says the flow is supersonic, right? And in the fourth point, it is saying that it is turning away, right? So if you add up these two information, right, what you see is one should get expansion waves, right? So then question says that it is expanding. That is correct. But then in the third point, the question says that the Mach number is reducing, right? So if there is expansion, and also we have this just discussed in the expansion waves, if there is expansion, right, the Mach number increases, right? The point that Mach number is reducing, as has been mentioned in this particular question, doesn't add up to the whole scenario, right? So this is the odd one out, right? Had the question been, had the question said that it is increasing, then it would have been, nothing would have been wrong in it. But as the question says that the Mach number is lowering down, right? That is not true, right? So the correct answer is false, right? So Jen is correct. The answer is, if you see the answer also, it is B, right? Okay. So the first question was based on oblique shocks, and then in this question we saw expansion wave. Okay, then let's move on to next question. Again, the topic is concept of expansion wave, right? You can write concepts of expansion wave, right? Also, like on the same thing, right? So this is concept of expansion wave. Topic is the concept of expansion wave. So this question says, third question, this is third question, and it says, when a body moves at supersonic speed, then, so there is a body that is moving with supersonic speed, and all the information related to its flow properties, such as pressure, temperature, density, etc., can propagate upstream. Right. So the question says there is body, we have a body, it is moving with some speed, that is supersonic, right? Then the question says then all the information related to its flow properties. So then there is information, right, related to flow properties. So the flow in which this body is moving, the properties of that particular flow, right? In terms of pressure, temperature, and density. which we have been discussing about, right? In normal shocks also, and in oblique shocks also, expansion waves here also we are discussing this, right? So then all the information related to its flow properties, pressure, temperature, density can propagate. So we want these properties to propagate upstream, right? So what are the options? It's a true and false type of question. So does this
False.
happen? False. Okay. Jenny says it's false. Sorry. Okay. So this particular concept we discussed in normal shocks also, right? But then here also we will discuss this, right? Because it's pretty important topic, right? From the perspective of fundamentals, right? Fundamentals of compressible flow. From that perspective, this particular concept is very important. So we should be able to visualize this, right? So the flow is supersonic, first of all. Then all the information related to its flow properties, right? Can they propagate? What is this? Sorry. So what is this essentially saying is that, so if there is this body, right? Let's say this is our body, and let's say, oh, I'll draw this on here, right? So this is question 3, right? Solution. So if there is this body, let's say it is moving in this direction, right? So because this is moving in this direction, it will send pressure waves, right? Because this movement is behaving like a disturbance in that particular flow, and this particular disturbance has to be communicated in the flow, right? So let us say there is pressure disturbance here, right? So it will propagate in all the directions, right? In this way, right? But then what is happening is this is also moving in this direction, right? And this wave has velocity, right? Let us say this is subsonic, right? For the sake of understanding, let us say this is subsonic. The question says it's supersonic. So let's say this is subsonic. So all right. So what will happen? This pressure wave will keep on moving, right? So let us say if this is the initial, this at some time t, let's say this is time t, right? And then it moved to this position, right? This is position 1 and this is position 2, right? So taking this particular point, first point as center, let's just, oh my god, let's just draw a circle, right? So this is with respect to point 1, right? Okay. So in this time, this particular this reaches particular this body reaches in point 2, right? So from there it starts communicating to the flow, right? But then what happens is that this communication cannot go faster than the speed of sound, right? Because the flow is subsonic, right? The body is subsonic, right? So this particular object in any case won't be able to move out of this disturbance of its previous case, right? Because the speed of the propagation of wave is greater than the speed of body, right? So if at delta t it is reaching at this point, right? So let's say this is t1, right? And this is t2. And let's say there is another further point t3 where t3 is greater than t2, right? So what happens is there are these 2 points, right? So the disturbance for one will again increase, right? So there will be another bigger circle, right? But then there will be circle for this also. For this is this circle was for first, and then there will be some circle for this particular uh, uh, body, right? Second body. So if this again decides to move ahead, so in that case, this circle for this second pressure wave, right, and for the first this pressure wave, these again will increase. In that case, even if the body moves in this direction, in that case also there is no chance that this particular body is moving out, crossing that this sound barrier, right? All right. But then if this if this is opposite, right? If the speed of propagation of wave is less than the speed of body, in that case we see structures like this. Sorry. Right. We see structures like this, right? So why we see such structures, right? Because let us suppose the body is at this point, right? And it is moving in this particular direction, right? So at some point, or not at some point, from the initial point only, it is this body will move, just cross the this barrier, this sound barrier, right? These are sound barriers. You can call this as sound barrier, or you can call it a pressure wave, right? This is up to you, right? Because this is the moving this pressure wave is moving with the speed of sound, right? So in that case it crosses this sound barrier, right? And what we get this is a Mach wave, right? So because the flow is supersonic, right? Right. So what was happening is there that because for subsonic case, this object always remains behind of this disturbance. So in that case, we can say that the propagation is upstream. There is propagation upstream, right? Because this if you see this point, right? If you see this point, this is ahead of this particular object, right? But if you see here, in that case, this is our some disturbance, and this object has escaped that this propagation this wave, right? And in that case, this propagation won't be able to move upstream, right? If this barrier, right, if this barrier had been ahead of this particular object, then it would have been that this is disturbance is communication of this disturbance is ahead of this object, but that is not the case with the supersonic flows, right? So this was about this particular question, right? Question number third, right? So it cannot propagate upstream, so that's why this question is false, right? Okay, so let's move on to next question, right? Or let's take a 5 minutes break quickly, right? Because it's four only. So let's just take a 5 minutes break, and then we'll quickly, because we are left with 10 this theory based questions, and then there are three numericals also.
Okay.
So we'll try to compress all that in this remaining time, right? All right. Okay. Okay, then let's continue with the session. Okay. Okay. Left with. Okay. All right. So the question is from the formation of expansion waves. All right. So this is the modeling of expansion waves part, right? So the question says, what does the propagation of an expansion wave in a medium leads to? Okay. So this is basically the propagation of an expansion wave. So as I was discussing the modeling of this by means of this piston example, the modeling of expansion waves I have discussed, right? So I believe the question is based on that only. Okay. Okay. So this is yes, right. Before I start saying anything, just try to answer this.
Pressure and temperature drop.
Okay. So you're saying these both options are right. All right. So yes, right. So in normal shocks, what was happening is that so from the modeling of normal shock waves, we saw that these were coalescing, right? These normal shocks were coalescing, and then the uh, pressure was increasing in that case, and the static temperature was also increasing in that case, right? And static density was also increasing in that case. And for the expansion waves, if we see, then the things are totally opposite from normal shocks. So there is this static pressure drop, there is static temperature drop, right? But if you see the total uh, pressure or total temperature, so in normal shocks, what was happening is that the pressure was uh, total pressure was decreasing, right? And then total temperature remained constant, right? Right. For normal shocks, P naught 1 was greater than P naught 2, right? So there were pressure losses, and then but there was no energy loss, right? Energy was totally conserved. But for expansion cases, this is the case, right? So there are no pressure losses, and then for the temperature, the case is the same as was for normal shocks, right? So this is about expansion wave, right? Flow properties, right? Of in case of expansion waves. So obviously the static this properties will drop, right? But then what happens with the total such properties, right? The total case of these properties. So that we should also know. All, all right. So let's move on to next question. Formation of expansion waves. Right. So in a series of expansion waves, the tail of the wave has less speed than the head of the wave. Yes. Sorry. So in this question, one must know what is the head and what is the tail of an expansion wave. Only then you'll be able to answer this question. If you don't know, then there are chances 50-50 chances, because either of the side would have to be one of these two terms, right? So, yes, true or false?
True.
True. All right. So it is this case only. Okay. So this was our first expansion wave and this was our second expansion wave. So here also I have this written this, the velocity of this expansion wave 1 would be greater than the velocity of expansion wave 2, right? So okay, right. So yes, you're right that the velocity would be less for the case that is late in terms of initiation of a particular expansion wave, right? But then you should parallelly, this should be like move in your mind about this normal shock condition also. Okay, so you're right, it's true. All right, and let's move on to next question. Sorry. Okay, across an expansion wave there is, yes, already discussed this, right? I'll just again write this. This is 1, this is 2, and this is our fan, right? So I'll write static properties. What happens for static properties? 2 is less than 1, right? What happens to total properties? 2 is equal to 1, right? For the total properties, there is no change, right? So there is decrease, right? Across an expansion wave, there is decrease in static pressure. All right. Okay, this you know, right? Okay, let's move on to next question. So this is again based on this properties only, right? So across an expansion wave, there is dash in density. Okay. Obviously, I should have written static or total, but here I mean static, right? So same is the answer for this case also, right? There will be decrease in, right, density, because it's expansion, so there will pressure will decrease, density will decrease, temperature will decrease. Okay, let's move on to next question. Yes, answer this question. The question is from fundamental equations of Prandtl-Meyer waves, right? This question is on Prandtl-Meyer function, right? So if you know the Prandtl-Meyer function, you know the answer.
B.
B or D? This one or this one?
B.
This one.
Yes, B. Upstream Magnum.
Upstream Mach number only. Okay. I'll write this one. Yes. This is question. Right. Only two terms, right, are included in this particular function. One is this Mach number, and then there is this specific heat ratios also there. Okay, Ginny?
Okay.
Yeah. But majorly, right, you're right that this Mach number, it majorly depends on Mach number, but then we cannot take this gamma value to be always 1.4 or some particular value, so it can change in that scenario. In this whole situation will change, right? But in any case, if somebody has to give a question based on this function, they usually they like uh, give this particular function, all right? So, but then if you have remembered this, then it is good for you. In that, like in some case, if somebody has not given this particular function, in that case, it's good for you. Otherwise, most of the cases they give this expression, right? All right. So answer to this question is D, right? Okay. So you're partially correct, right? Then specific heat ratio is also there. Okay. Sorry. So normal shock versus oblique shock that I have been doing in this whole duration of the session. All right. Which of the statements, sorry, which of the statements is True. Right. Yes. Please read the statements carefully and let me know the answer. No answer. Okay. Then let me answer this, right? So if we see the pattern of the options, right? So if you see, then these statements are almost similar. Okay. So, but few things have been like changed or tweaked, right? So if you see, let's take one this statement, right? The normal shock waves are a special case of oblique shock waves in which the streamlines are parallel to the shock waves. This is the first statement, right? The second statement is normal shock waves are a special case of oblique shock waves in which the streamlines are perpendicular to the shock. So A and B are similar, right? But there's a difference of perpendicular, right? Now if you see C and D, so also in A and B there is this normal shock and this oblique shock. So a comparison has been done between the two, right? So if you see C option, there is this instead of normal shock wave, they have introduced oblique shock wave, right? So the oblique shock waves are a special case. Now they are saying that oblique shock waves are a special case. So the question is about which shock wave is a bigger umbrella term, right? Whether it is this normal shock wave is the umbrella concept, right? Or whether the oblique shocks are the this umbrella concept, right? So in this A and B and C and D, this is the like difference, right? So if you see in C, the oblique shocks are a special case of normal shock, right? So in that case, the option says that the normal shock is the umbrella term, right? If you see the option D, there also the first oblique shock has been introduced and normal shock has been introduced, right? So the question says in this in these two cases, right? In these two cases, this is the uh, normal shock is the umbrella term, right? This is the umbrella term, umbrella term. And in these two options, this oblique shocks is the umbrella term, right? So, but if we see both normal shocks and oblique shocks, right? Normal shock is one case, right? But if you see oblique shocks, right? In oblique shocks, there is this turning of the wedge, right? You turn the flow, right, with some angle theta. So if you keep on increase for a particular Mach, if you keep on increasing this theta, so beta increases with that. Beta is nothing but the shock wave angle, right? I hope you are able to visualize this, right? Sorry, this. You see, this is theta, right? And this is your shock wave, right? And this bigger angle is your beta. So if you keep on increasing the theta, the beta will also keep on increasing. And a value of theta comes when the beta becomes 90 degree, right? When the beta becomes 90 degree, in that case, we have this normal shock wave condition, right? So normal shock wave is a special case of oblique shock waves, right? Where the shock wave is perpendicular to the streamline, right? In no case it is there that the shock waves are parallel to the streamlines. Either there is some oblique, there is some angle to the streamlines, or it is totally perpendicular to the streamline, right? There are two cases only, either broad cases, either this is oblique or this is perpendicular. There is no case in which the flow is moving in this direction and the shock is also this direction. This doesn't make sense, right? So if we see that, take these points into consideration. In that case, if you see option B, right, the streamlines are perpendicular to the shock waves, right, and the normal shock is a special case of oblique shock. So this is the correct statement, right? All right, let's move on to next question. Okay, so the oblique shock waves are analyzed in dash flow field. Yes. So if you see normal shock waves, they are analyzed in particular dimension, right? Either 1, 2, or 3D, right? And then oblique shocks are also analyzed in particular number of dimensions, right? So what is the answer for normal shock waves and for oblique shock waves? The question is only for oblique shock waves, but yes. No answer. All right. So for normal shock waves, all right, there is flow in one direction. Okay. And then there is this shock also is perpendicular to these streamlines, and we are concerned with only one direction, right? One direction of these normal flow, right? So there is no second dimension that we need to consider when we are dealing with normal shock waves. But in case of oblique shock waves, so we have done this 1D analysis also in case of normal shock waves, but in case of oblique shock waves, right? So because there is this obliqueness, right? So we need to consider one more direction in case of these oblique shocks, because by just means of only 1D one dimension, we won't be able to express these oblique shocks, right? So in that scenario, we add one more dimension in our analysis to complete the analysis, right? So option B is correct for this particular question. All right. Okay. So, okay. Right. Then let's move on to next question. So stagnation pressure across an oblique shock. What happens to stagnation pressure across an oblique shock? Yes, please try to answer this. So I have mentioned about expansion waves. What happens to the stagnation properties in case of expansion waves, which is they remain constant, right? But what happens in this case? Please let me know.
Decrease.
Decreases. All right. Yes, you're right, because it's also okay. Like this was happening in normal shock waves also, that the total pressure was decreasing and there were pressure losses. So oblique shock is also in that line only, right? Essentially, it's a shock wave, right? And across this, because uh, across this there is this drop in the total pressure value, stagnation pressure value. So you're right that it decreases, right? Okay. Then there is this topic Mach angle versus shock wave angle. Okay. So the question says Mach wave is the limiting case for oblique shock. That is, it is an infinitely weak oblique shock. Yes. Please answer this. Whether it is true or false.
True.
All right. Okay. So you're right. So Mach wave is the weakest form of an oblique shock, right? Okay. So if you see, it has been drawn like this. So it is being drawn like this, right? So if this is the flow direction, then this becomes your, if your flow is moving with uh, sonic Mach, right? So this is the case for, and this is the case for beta is the case for oblique shocks, and there is this limiting case. Yes, smallest beta value, that is this mu m, right? So this is the limiting case for oblique shocks. Okay, answer A is correct. Now moving on to next question. Shock wave angle for a normal shock is, okay. Yes, answer this. This is a nice question. I hope you know what is a shock wave angle is, right? Beta. I'm talking about beta in case of oblique shocks.
90 degree.
Yes. Great. All right. So we are done with these conceptual questions, right? Now we will move on to numerical questions. So we have 25 minutes in hand. So we will keep our speed accordingly, right? 3 questions are in hand. We'll try to solve these 3 questions. Okay, first question is theta beta m relation. Then second question is, okay, this is Prandtl-Meyer. Third question would require a discussion. Right. Okay. C, the correct option. Yes, it's on oblique shocks. And the question says that find the deflection angle of an oblique shock wave if the upstream Mach number is 3 and the shock wave angle is 30 degree. So what has been given in the question? Upstream Mach number is given. You write it m1 or m is 3 and beta is what? Beta is 30 degrees, right? And gamma is 1.4. All right. So question number 14 solution. M is 3, beta is 30 degree, and gamma is 1.4, right? So we will be using theta beta m relation, which is tan theta equals to 2 cot beta m1 square. Let's write it m1 square sine square beta minus 1 divided by m1 square gamma plus cos 2 beta. Please check this expression if this is right, because I have solved based on this expression only. So now we are going to find this, right? Yes, please solve this. I'm also solving this. Sorry. Okay. Yes. Please check this. Yes, Ginny, are you able to get this answer? Hello, Ginny, are you there?
Yes, yes.
Yes, you got this answer.
Yes.
All right. Okay, great. Then there is next question. So the answer to is this problem is 12.77 degrees, right? Option B.
Yes.
All right.
12.778 I got this.
Yeah, great. 12.77. Okay, okay. All right. Then there is next question. Find out, this is on Prandtl-Meyer function. So find out the fan angle of an expansion fan if the upstream and downstream Mach numbers are 2 and 4 respectively. All right. So as here we can see that the Mach number is increasing across this expansion fan, right? And gamma has been given as 1.4. So let's quickly solve this problem also. So M1 is 2 and M2 is 4, right? And then we need to find gamma is given as 1.4 and we need to find out expansion fan that is represented by phi. So using the Prandtl-Meyer, yes, you want to say something?
No. Can you
Gamma,
show the questions?
yes, 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 yes. See this.
Okay.
Okay, thank you. So we have this Prandtl-Meyer functions expression we have, right? All right. Gamma plus 1 over gamma minus 1 tan inverse of. So I believe I have written this, right? I've already written this previously here, right? Let's see. So this here, no, sorry, I've written somewhere. Okay, it has been written somewhere in the previous slide, so I'll again just write this expression down. So n equals to, if you know the expression, you can just continue with the calculation. I'll just write root. So this is the formula, right? Okay. So we need to find this fan angle, right? So if you see this, this is this forward Mach line and this is rearward Mach line, right? So this one is mu m1 and this one is mu m2. This angle is phi that we need to find out, and this is theta, right? So so if you see the phi, this is, so if you reduce, if you see this angle, right? Let's say this is x angle, right? If you subtract x from this mu m1, we get phi, right? But what is x? If you see x, what is x? X is nothing but mu m2 minus theta, right? So if we put this here, what we get? We get phi is mu m1, right, minus mu m2 minus theta, or mu m1 minus mu m2 plus theta, right? So this is our expression for fan angle, right? Right. But we know theta, right? The question is, do we know theta here? We don't know theta. But what is theta? Theta is mu m2 minus nu m1, right? Nu m1. So this news formula is from Prandtl-Meyer, this function, right? So if you calculate nu m1, which is nu 2, what you get? If you calculate this, you get 26.3797, right? Because I have calculated it, I'm just writing it as it is. But you can use this formula to get to this value, right? And the same way, nu 4, if you calculate, right, it comes out to be 65.7848, right? And if you want to calculate mu1, that is 1 by m1, right? So that is sine inverse of 1 by 2, which will come out to be 30 degrees, right? And if you calculate mu m2, sine inverse of 1 by m2, which is sine inverse of 1 by 4. If you calculate this, it will come out to be 14.4775 degrees, right? Right. From here, what we can get is theta, right? Theta here is mu m2 minus mu m1. So that comes out to be 39.4051, right? So we have theta, we have mu1, mu m1, mu m2. We can get phi, right? Phi is, see, phi is mu m1, which is 30 degrees, right? Minus mu m2, which is 14.4775 degrees, plus theta. Theta is 39.4051 degrees, right? All right. So if we calculate this, we get 54.9 9276 degrees, right? So this is the fan angle 59.92 or 93, right? So this comes out to be 59.93 degrees. 54, sorry. Right? Yes, Ginny, were you able to follow this particular numerical?
Yes.
All right, great. That is great. Thank you. So, last question of this session, right? We are left with 7 minutes, and that is not, I believe, sufficient, but then we shall will have to compress it to that time. All right. So if you see the options, so C option is correct, right? 54.93. All right. So So question is now on oblique shock relations, right? For an oblique shock wave, upstream Mach number and shock wave angle are given as 1.5 and 45 degrees respectively. Upstream Mach for an oblique shock, right? M1 is given as 1.5. And then beta is given as shock wave angle, right? Shock wave angle is beta. Upstream Mach number is M1. Is given as 45 degrees. Find M2. We need to find M2. Yes, how do we find this? Can I move on to solving this question, please?
Yes.
Yes, okay. All right. So what has been given? M1 has been given as 1.5, right? And also beta has been given as 45 degrees. So what we will do is, so if wait, yes, right. So if you see, just wait a second. Right. So what we will do is, because we need to find M2, right? What is M2? So if you see, M2 is theta, right? This is the expression for this M2, right? In terms of these components of this shock wave or flow direction across a oblique shock. So I had to draw this figure, I had to explain this figure, but because we are short of time, so I'll just tell you the steps that we need to follow to solve this question, right? So this is for M2, this is expression, right? But here we don't have Mn2, right? We don't have beta. We have beta, but we don't have this theta. We don't have. We have beta, right? But we know Mn2 can be solved, right? Using these two values, because Mn2 square is Mn1 square plus 2 by gamma minus 1, right? At 2 gamma, I'm just moving in reverse direction, right? From what I know of M2, I'm just trying to get to my answer, right? So now if you see, this is Mn2, right? But in this Mn2, what do we know? We do we know Mn1? No, we don't know Mn1. We do know gamma, right? Gamma is in our hand 1.4, but we know Mn1? No, right? But then if you see this expression, right? if you see this expression, here we know m1, we know sine beta, right? We can find out m1, right? So this way we can find out what mn2. This is for mn2 only, right? Right. So for mn2, you need what? You need to first find out mn1, right? And then from there you can find out this uh, mn1 you can find out from this. All right, I should not. It will confuse you. All right. So this is for mn2, right? But then in m2s, because we need to find out eventually we need to find out m2, right? So we can somehow calculate mn2, right? But then we don't have theta in our hand, right? So for that, if you see the theta beta m relation, right? In this, we do we know m? We do know m. Do we know beta? We do know beta, but do we know theta? We don't know theta. So uh, we have also done like this numerical of based on theta beta m relation, right? So from that we can find out this theta, right? So if we are able to find out theta, then we are done with this question, right? So I'll just write down these calculated values, right? So when you find out, first you find out mn1, right? So it comes out to be 1.0606, right? From there you find out mn2 square, which comes out to be 0.8910, right? And so mn2 comes out to be 0.9439, right? Then you use the theta beta m relation. This is for mn2. This is step 1. You consider as this as step 1 for mn2. Then step 2, you have to get theta. So using theta beta m relation, you get tan theta equals to 0.0485, right? And which means theta comes out to be 2.7766 degrees, right? This is step 2. All right. Okay. Right. Now we know what m2 is. m2 is mn2 by sine beta minus theta, right? mn2 is 0.9439. Sine beta minus theta is 45 degrees minus 2.7766 degrees, right? So which is 42.2234. So it comes out to 1.4045. All right. So we had this m1 as 1.5, and from there, so it's a kind of weak weak oblique shock, right? In which from 1.5 the Mach has reduced to 1.4. Also, this point is to be noted that when we move across a normal shock, so the flow do remains sonic, supersonic, but then from its upstream value, it reduces to some value. All right. So this was about this question. So Ginny, again, were you able to follow this question? Because I have moved in a very quick manner.
Yes, yes.
All right. All right. Okay, then we are done with the planned questions of this particular session. All right, so I'll conclude this way that we initially discussed the topics related to week 6, right? Then we moved on to questions, conceptual questions, Total 13 questions we discussed based on the week 6 content. Then we did three numericals, right? Two were on oblique shock relations and one was on expansion waves, this Prandtl-Meyer relation, right? And this way we did our today's session. All right. So now I shall like finish this session. All right. We shall end this session and we shall move in. But we shall meet in next such session, right? Week 7 with the content and questions related to week 7. We shall meet in the next week on same day, same time, right? Sunday, 3 to 5 p.m. Okay, then.
Okay, thank you.
Thank you.